Today our focus is looking at independent and non-independent events. So if you recall from chapter 14, when A and B are independent, it meant that one event doesn't affect the outcome of the other. Then the probability of A and B, there was our magic word and, we learned that and meant multiply. So the probability of A and B was the probability of A times the probability of B. That's what we learned in chapter 14. It was very straightforward. We learned that and meant multiply. And in chapter 14, that's all we had to worry about because they were independent. Chapter 15, we are now changing that. Now, when A and B are not independent, that means that whatever happened first affects the second one. Then the probability of A and B changes. We still have multiplication, but we have to use some common sense. There's going to be two versions. The probability of A and B will equal the probability of A happening, and means times, but now when we find the probability of B, we have to know up front that we are given A already happened. So that probability is not going to be straightforward. It's going to be different. We're going to have to use that same conditional idea from the last lesson. The other version is the probability of A and B is the probability of B happening first, then the probability of trying to find A given B has already happened. So these two versions, it just depends upon which one happened first. If A happens first on this first one, then it's the given. If B happens first on the second one, then B is the given. So let's take a look at an example with these new formulas. 70% of the time, the sun is shining, and 4% of the sunny days, it rains. What is the probability that it is sunny outside and it is raining? So the probability of sunny and raining. So we're going to let, obviously sunny is A, raining is B. The question is, which one do we know happened first? It says 70% of the time the sun is shining, and 4% of the sunny days, it starts raining. So it's sunny to start with, then it rains. So the sunny is happening first. So what's just the probability that it is sunny outside? Times, so that's the one that happens first. Then we're going to find the probability that it's raining given it is sunny. So the probability that it's sunny outside, 70% of the time the sun is shining, that would be 0.70. Times, we need to find the probability that it's raining knowing that it was sunny to start with. Well, if you look at that other number, it says 4% of the sunny days, it rains. That is this percentage because we are being told 4% of all of the sunny days, it rains. So we're going to multiply it by 0.04, and 0.70 times 0.04 is 0.028. Now that one was a little not quite straightforward. Examples 13 and 14 focus on the exact same concept. This is really where the idea of not being independent comes into play. So we're going to look at 13 together, and then you guys are going to do a little bit of 14 on your own. You are picking 3 cards, one at a time, from a standard deck of 52 cards. The big key here is without replacing the cards. Every time you draw a card, the deck is now different. Now, if you struggle with card probabilities, in class, ask to borrow a deck of cards so you can physically see what cards you're working with. So our first question we're trying to answer is find the probability that all of the cards are diamonds. So we're simply going to start with the first part. It was saying, well, what's the probability that the very first card out of the deck we draw is a diamond? Well, how many diamonds are in a deck of cards? That would be 13. How many total cards are in the deck? 52. That's just the first card. Now, here's what's happening. We're drawing a card out of the deck. We are going to make the assumption that we drew a diamond. So I now have a diamond out of the deck. It's not going back into the deck. So now, knowing that I have a diamond sitting off to the side, I now need to find the probability that the second card is also a diamond. So we're going to multiply because this is always multiplication. So how many diamonds are now left in the deck? It's no longer 13. It is now 12. How many cards are now in the deck? It's not 52. It's now 51. So we actually drew the card. Guess what? We assume it's another diamond. So now we have 2 diamonds sitting off to the side. Now, because we're drawing 3 cards, we now need to have a third fraction. Again, what is the probability that we draw a diamond? Well, how many diamonds are left in the deck now? Well, that's 11, because we've drawn 2 of them out. How many cards are left in the deck? That's 50, because again, we drew 2 of them out. So here's where you need to be smart. Do not try and multiply all of this in the calculator at one time. You need to practice reducing the fractions separately. The first fraction I'm going to look at is the 13 over 52. I know those are both divisible by 13. So I'm going to cross them both off. 13 goes into 52 4 times. The next thing I'm going to look at is the next fraction, 12 and 51. Well, 3 goes into both of those. 3 goes into 12 4 times. 3 goes into 51 17 times. The third fraction, nothing I can do to start with. Is there, now looking at all of the red numbers, is there any numbers that can still be reduced maybe diagonally? Well, if you notice, there's a 4 on the top by the 12, and there's a 4 on the bottom by the 52. Well, those 4 goes into both of them. I'm going to cancel those 2 4s out. So the only number I have left on the top is 11. Can 11 cancel with 17? No. Can 11 cancel with 50? No. Now we're ready to multiply. 11 is your numerator. 17 times 50 is 850, and that is reduced. So now we're going to start the deck over. All of your cards are back in the decks. We're back to 52. So now we want to know what's the probability that we are drawing a 4. Okay, well, let's start there. How many 4s are in the deck? Well, there's 4 4s in the deck. How many cards are in the deck? 52. So when we draw the first card, we are going to assume that we drew a 4. So there is now a 4 sitting off to the side. Now we want to find the probability, multiply, that we get a queen. Well, remember, there's a 4 off to the side. So how many queens are in the deck? There's still 4 queens. But how many cards are in the deck? There's no longer 52. There's 51 because we took one of those 4s out. So now we've drawn the second card. Since we were focused on a queen, it's a queen. Now off to the side, we have a 4 and a queen. Now we got our third fraction. Now what's the probability that we draw a 4 again? Well, how many 4s are in the deck? We've taken one out, so there's 3 4s left in the deck. How many cards are in the deck? Well, we've already taken 2 cards out, so there's 50 cards in the deck. So let's start doing some reducing. 4 and 52. Those can both be divided by 4. That leaves us with a 1. And 52 divided by 4 is 13. Can 4 and 51 be divided by anything? The answer there is no. Can 3 and 50 be divided by anything? No. But we can do some diagonal. 4 and 50 are both even. They can both be divided by 2. So 4 divided by 2 is 2, and 50 divided by 2 is 25. 3 and 51 can both be divided by 3. 3 divided by 3 is 1. 51 divided by 3 is 17. The only number left in the top is a 2, and none of the numbers left in the bottom are even, so we're done. 1 times 2 times 1 is 2. 13 times 17 times 25 is 5,525, and yes, that's reduced. Let's look at another one. What's the probability that you draw no black cards? So nothing black. By the way, all the cards are back in the deck. So how many cards in the deck are not black? Well, if you know your cards, 26 are black, 26 are red. So 26 cards are not black out of 52. So we draw a card out. It is not black. It's red. We set it off to the side. New fraction. We need another card that is not black. Well, we had 26. One of them was just taken out, so we're down to 25 out of now 51. We draw a card. It's not black. We set it off to the side. So now there's 2 cards that are not black sitting off to the side. We need a third card that's not black. How many cards are not black still? 24, because we've taken out 2 of them. And there are now 50 cards in the deck because we've taken out 2 of them. Let's do some reducing. This first fraction, 26 goes into 52. So 26 divided by 26 is 1. 52 divided by 26 is 2. 25 and 51 cannot be reduced. 24 and 50 can both be reduced by 2. 24 divided by 2 is 12. 50 divided by 2 is 25. What else now can we do diagonally? Well, right away, we see a 25 on the top and a 25 on the bottom. I'm going to cancel those 2 25s. Can 12 be reduced with anything? Well, 12 can be reduced with the 2 way over here. So I'm going to cross off the 2 and the 12. They can both be reduced by 2. 2 divided by 2 is 1. 12 divided by 2 is 6. And yes, there's actually one more canceling that we can do. The 6 and the 51 can both be divided by 3. 6 divided by 3 is 2, and 51 divided by 3 is 17. And so the only number that we have left on the top looks like is 2, and the only number we have left on the bottom is 17, and that's reduced. Let's look at the last part of this example. You want to know the probability that you draw at least one jack. So here's the question that's going to be the most confusing. We've seen this phrase at least one before. We talked about at least one. We hate that statement because there's lots and lots of cases. So we always use the complement. So our focus is going to be no jacks. And so we need to start by finding the probability that there are no jacks being drawn. So we start with a fresh deck. How many cards in the deck are not jacks? Well, there's only 4 cards that are jacks, so 48 cards out of 52 are not jacks. Okay, well, guess what? We pulled out a jack. And so now that we've pulled out a jack, we need to focus, we pulled out a card that is not a jack. Now we need to find another card that is not a jack. Well, how many of those are left? There's 47 of them left because we took one out. How many cards are still left in the deck? 51. Okay, so we drew a card. Guess what? It was not a jack. So now we need to find a third card that is not a jack. That leaves us with 46 cards that are not jacks out of 50. So we need to do a whole bunch of canceling. Let's start with the first fraction. 48 and 52 are both divisible by 4. So 48 divided by 4 leaves us with 12. 52 divided by 4 leaves us with 13. 47 and 51 cannot be divided. 46 and 50 can both be divided by 2. So we have 46 divided by 2 is 23. 50 divided by 2 is 25. Can anything else be reduced? Well, if we look, we have a 12. 12 and 13 cannot be reduced, but 12 and 51 can. 12 and 51 are both divisible by 3. 12 divided by 3 is 4, and 51 divided by 3 is 17. And yes, that is as far as we can go. So we got some multiplying to do. We need to take 4 times 47 times 23, and we end up with 4,324. And 13 times 17 times 25 leaves us with 5,525. Now, here's the thing. This was not the question we were asked to do. We were asked to find the probability that we draw at least one jack. Anytime we use the complement, we always take 1 minus the answer we found. The 4324 over, whoa, I ran out of space. Let's move that up. The 4324 over 5525. If you have a calculator, you can simply take 1 minus those fractions, hit math, enter, and it will give you the fraction 1201 out of 55. I do not like that that's not fitting. Sorry, guys. Our final answer is 1201 out of 5525. Okay, so let's take a look at the final slide. So here's the ones I would like you to try. I would like you to try A and B on your own. So pause the video, try those, and let's see how you did on just those. A bag of marbles contains 5 red, 4 blue, 3 green, and 8 orange. You are drawing 2 marbles without replacement. So first of all, you need to find out how many marbles were in that full bag. 5 plus 4 plus 3 plus 8 was a total of 20. So what was the probability of drawing 2 green marbles? Well, you should have said the probability of drawing the first green marble. There's 3 green out of 20 marbles. We drew a green out. We set it off to the side. What's the probability of drawing another green marble? No longer 3 out of 20. It drops to 2 out of 19. What were you able to reduce here? The only thing you should have been able to reduce was the 2 and the 20, and that should have reduced to 1 and 10. Your final answer should have been 3 out of 190. So hopefully you did that first problem right on your own. Let's try the second one on your own. Drawing your first orange marble on the second draw. So if your first orange is on the second draw, that means that you did not have an orange on the first draw. Then you had an orange on the second draw. I know, a little wordy. What's the probability of not getting an orange on the first draw? Well, 5 red plus 4 blue plus 3 green is 12 marbles out of 20 that are not orange. So we drew out a marble. It's one of those not orange colors. So now we're switching to orange. Now, what's the probability that we do draw an orange marble? Well, there's still 8 orange, but now there's only 19 in the bag. So what can we reduce? Well, let's start with 12 and 20. 12 and 20 are definitely both divisible by 4. 12 divided by 4 is 3. 20 divided by 4 is 5. And at this point, nothing else can be reduced. 8 and 19 cannot, and nothing can work diagonal. So we're ready to multiply. 3 times 8 is 24. 5 times 19 is 95. Okay, so those were the two that I wanted you to try on your own. Let's look at the two that we're going to do together. What's the probability of drawing only one red marble? Notice, I gave a little hint there. It says it can be either the first or the second draw. There's an or. Or means that we're actually going to be looking at more than one case. So the first thing we're going to focus on is what's the probability that we draw a red marble on the first draw. But again, we can only have one red. So the first draw, red marble, how many reds do we have? There's 5 out of 20. Well, this guy has to have a second draw because we're drawing 2 marbles. But the second marble cannot be a red. So how many marbles are not red? Well, 4 plus 3 plus 8 is 15. But because we drew a red marble on the first time, there's only 19 marbles left. This is case number 1. This is red on the first draw, not red on the second draw. Now we got to do this or thing. That means add. And we have a second case, drawing a red marble on the second draw. So now the first marble is not red. So that was the blue, the green, and the orange, which was 15 out of 20. We drew out one of those other colors. Now we're focused on drawing out a red because we need a red now on the second draw. Well, that would be 5 red that still are in the bag, but it's out of 19. So let's look at some reducing. This first case, because the plus sign, you can't cancel with the plus sign, so you can only cancel on each side. This first fraction, 5 and 20, can definitely be reduced by 5 to 1 out of 4. And 15 out of 19 cannot be reduced. The second side of the plus sign, the 15 and the 20, can definitely be reduced, also by 5. So we're left with 3 and 4. So let's see. The first fraction, 1 times 15 is 15. 4 times 19 is 76. Plus 3 times 5 is 15. 4 times 19 is 76. Well, this is really nice. We have to add these fractions. They already have a common denominator. So 15 plus 15 is 30 out of 76. But that's not reduced. Our final answer for this entire problem, those can both be reduced by 2, is 15 out of 38. So this one was a little tougher because we had 2 cases. You could draw that red marble the first time, or you could draw the red marble the second time. Now, last question. What's the probability that at least one of the marbles is blue? There's that silly at least thing. So we're going to focus on, instead of at least one blue, we're going to focus on no blues. Well, what's the probability that the first marble is not a blue marble? Well, the 5 red plus the 3 green plus the 8 orange is 16 marbles that are not blue out of 20. So we drew out one of those marbles. One of the ones that is not blue is off to the side. What's the probability that we get another not blue marble? Well, there was 16, now there's 15. And there was 20, now there's 19. So let's do some reducing. Well, I definitely know 16 and 20 can both be divided by 4. 16 divided by 4 is 4. 20 divided by 4 is 5. I also know that 5 and 15 can both be reduced by 5. 5 divided by 5 is 1. 15 divided by 5 is 3. And that is all we can do. 4 times 3 is 12. 1 times 19 is 19. But that's not our final answer because we used a complement. So we have to take 1 minus that answer of 12 over 19. If you have a fancy calculator, 1 minus 12 over 19 leaves you with 7 over 19 as your final answer. And that's the end of the lesson.